Hello, this is Professor Roman, and we continue our lectures on linear algebra with additional background information. We're now going to talk about equivalence relations and partitions. Informally speaking, a partition of a non-empty set S is just a collection of non-empty, non-overlapping subsets of the set S, whose union is the entire set. This is a picture, and the formal definition is really not much different from what I just said. A partition of a non-empty set S is a collection of subsets. I denoted them by B sub I, as I ranges over the index set capital I. They're called blocks of the partition, and the following properties must hold. The blocks must be non-empty, they must be pairwise disjoint, and the union of the blocks must be the entire set S. And we will denote the family of all partitions on a set S by PART of S. Here's an example of a partition of the real line into half-open intervals with integer endpoints, n to n plus 1. You can see from the picture it's fairly clearly a partition. The intervals are non-empty, they're non-overlapping, and their union is the whole real line. Now let's take a look at equivalence relations, beginning with the formal definition. A binary relation, which I'll denote by a tilde, on a non-empty set A is called an equivalence relation on A if it satisfies the following conditions. And this notation is read A is equivalent to B. So first we require reflexivity. Every element must be equivalent to itself. We require symmetry. A equivalent to B implies B equivalent to A. And transitivity. A equivalent to B, B equivalent to C implies A equivalent to C. And we'll denote the collection of all equivalence relations on a set A by EQU of A. Equality on a set is the prototype of all equivalence relations. Congruence mod K is also an equivalence relation on the integers. Now, as to the connection between partitions and equivalence relations, there is actually a one-to-one correspondence between the partitions of a non-empty set A and the equivalence relations on A. So let's first suppose we have a partition which looks like this, and here I haven't specified the number of blocks. There may be infinitely many or not. Then we can define what I call the same block equivalence relation on the set A, just exactly as it sounds. A is equivalent to B if A and B are in the same block of the partition. And it's quite easy to see that this is an equivalence relation. It's reflexive because every element's in the same block as itself. It's symmetric because if A is in the same block as B, then B obviously is in the same block as A, and similarly for transitivity. Now, it happens that all equivalence relations on a set A are same block equivalence relations. for an appropriate partition. And in fact, the map that sends a partition to its same block equivalence relation is a bijection between the partitions of A and the equivalence relations on A. Now, before we can prove that, we need to show how to produce a partition from an equivalence relation. It's the opposite process. So if we start with an equivalence relation on a set A, we need a definition. For each element little a in A, we define the equivalence class containing little a to be the set of all elements x in capital A that are equivalent to little a. This language, especially the words containing A, makes sense because of reflexivity. Every element's equivalent to itself, and so A does belong to the equivalence class containing A, which is a good thing, or we couldn't use the word containing. The element A is referred to as a representative of this equivalence class. There's another way to characterize equivalence classes that will be particularly important in a few minutes. We have an equivalence relation on a set A. An equivalence class, C, is a largest subset of A for which all elements in C are equivalent, but no elements outside of C in the set A minus C are equivalent to any element in C. So you can think of it this way. Take a single element in the set A and gather together everything equivalent to that element. Everything equivalent. That is an equivalence class. It's a largest subset of A for which all elements in C are equivalent. Now we can show that the collection of distinct equivalence classes forms the blocks of a partition. So we have an equivalence relation on a set A. Every element of A is in its own equivalence class. I already discussed that. It's because of the reflexivity of equivalence relations. Well, from that, it follows that an equivalence class is non-empty, and that the union of the equivalence classes is everything, the set capital A. If A and B are in the set A, then the equivalence classes containing A and B are equal if and only if A and B are equivalent. So this is a way to test for equality of equivalence classes. If we have two equivalence classes, then either they are equal or they are disjoint. Put another way, any two distinct equivalence classes are disjoint, and so the set of equivalence classes is pairwise disjoint, and that's the third property required of a partition. So the set of equivalence classes is a partition of the set A, and I'll call that the equivalence class partition associated to the equivalence class. So we've taken care of one. Let's look at the proof of two. First, we'll suppose that the two equivalence classes are equal. Then part one tells us that little a belongs to the equivalence class containing A, which is equal to the equivalence class containing B, and therefore A is equivalent to B. And that's one direction in this biconditional. For the converse, if A and B are equivalent, then A belongs to the equivalence class containing B as well. And so the entire equivalence class containing A is contained in the equivalence class containing B, because if we take an element from the, let's call it X, from the equivalence class containing A, then X is equivalent to A is equivalent to B, and so by transitivity, X is equivalent to B. In other words, X belongs to this equivalence class. So we have this set inclusion and a similar argument or an appeal to symmetry shows that the other inclusion, the reverse inclusion, holds, and so we have equality. For part 3, we have to show that distinct equivalence classes are disjoint. We can do that by showing that if these two equivalence classes are not disjoint, then they must be the same. Since they're not disjoint, there's an element X in their intersection. X is then equivalent to A, and X is equivalent to B, and so symmetry and transitivity show that A and B are equivalent. And therefore part 2 tells us that the equivalence classes are equal. So if two equivalence classes are not disjoint, they must be equal. And that completes the proof. You should notice that part 2 of this theorem, or at least a portion of part 2, B equivalent to A implies that two equivalence classes are equal, tells us there's a great deal of duplication in the way we write equivalence classes. In other words, in general, an equivalence class has a lot of representatives. Every element in the equivalence class is a representative and can be used to write the equivalence class. So if we take every element in A and form the equivalence class containing A, write this notation, we've got a lot of duplicates. This is a multi-set rather than a set. So we'll use this notation, P of the equivalence relation, P of partition, is this for the set of distinct equivalence classes. The brackets mean distinct. We have no multi-set notation, so we don't have to worry about that. No duplicates. Moreover, this theorem we just looked at says that the set of equivalence classes for an equivalence relation is a partition, the equivalence class partition. So if you look at this, here's a set A, take an element, take everything equivalent to it. If there's anything left in the set, take another element outside of this set, this subset, take everything equivalent to that element, and so on, and you will get a partition of A into distinct equivalence classes. For the equivalence relation of equality, for example, on a set A, the only element that belongs to the equivalence class containing little a is little a itself. It's the only thing equal to little a. So the equivalence classes are just the singleton sets. And the partition, the equivalence class partition, then is just the collection of all singleton sets, singleton subsets, if you want. That makes this partition the finest possible partition in the sense that each block is as small as possible. Blocks have to be non-empty, so they have to contain at least one element. Here's another example. We'll let A consist of all straight lines in the plane and define an equivalence relation on two lines by saying that L1 is equivalent to L2 if the two lines are parallel. That's easily seen to be an equivalence relation. The equivalence class containing a specific line L is the set of all lines that are parallel to L, which I obviously can't draw all the lines, but that gives you an idea here. So in effect, the equivalence classes specify the different directions in the plane. Now, let's look at the equivalence of partitions and equivalence relations. We know that a partition P of a set A defines the same block equivalence relation, and that gives us a map. And I've denoted this, I couldn't think of good symbols for it, so I simply denote it by same block ER. Maps partitions to equivalence relations. And specifically, it sends a partition to its same block equivalence relation. In the opposite direction, we know that an equivalence relation defines an equivalence class partition, so we have a function going in the other direction, which I denoted this way, that sends an equivalence relation to the equivalence class partition defined by that equivalence relation. Moreover, the compositions in both directions are identity maps. That means both of these maps are bijections, and in fact they are inverses of each other. And here is the proof. For this equation, we just take a look at this expression. It's the equivalence class partition of the same block equivalence relation. What do the equivalence classes look like for the same block equivalence relation? We have seen that one way to describe equivalence classes is as the largest subset for which all the elements are equivalent. So in this case, these equivalence classes are the largest subsets for which all elements are equivalent. No element outside of an equivalence class C is equivalent to any element inside C. And that implies that the same block equivalence relation, in other words, the collection of equivalence classes, is precisely the blocks of P. So we're just describing the blocks of the partition. Take the partition, the same block equivalence relation, though the equivalence classes are the biggest sets where everything's equivalent. So let's focus, say, on block A1 here. What's the biggest set? Let's take an element in A1. What's the biggest subset of A for which all the elements are equivalent to that element. Well, it's just the block, because this is the same block equivalence relation. For the other equation, this is the same block equivalence relation of the equivalence class partition. So if you look at the equivalence class partition, when are two elements equivalent? When they're in the same block. And when are they equivalent under the same block equivalence relation? When they're in the same block, which means they were equivalent under the original equivalence relation. So the same block equivalence relation is the same as the original equivalence relation. This proof is a lot of words, and these concepts are a little bit abstract, so don't be discouraged if all this seemed a little difficult to follow. It will be difficult to follow until you have some intuitive feeling for equivalence relations and partitions. Partitions fairly easy, but equivalence relations can be a little confusing. So you might want to go over the video a couple times, think about this, and you'll get it sorted out. This theorem is very important, though, because it says that partitions and equivalence relations are simply two ways of looking at the same concept. Partitions, on the one hand, are pretty easily pictured in the mind's eye. You can close your eyes and see a partition, these figures I've drawn. I didn't draw any figures for equivalence relations. They're a little less intuitive. So the fact that these are equivalent ideas is quite useful. There are times, in fact, when we start with one of these viewpoints and discover that it's simpler or clearer to switch to the other viewpoint. So both viewpoints have their advantages and disadvantages. Now let's discuss the real significance of equivalence relations in mathematics. It is often the case in mathematics that we want different formal expressions to represent the same mathematical object. For example, 1 over 2 and 2 over 4 are formal expressions. I'm treating them as formal expressions. Pretend for a minute that you do not know what a rational number is. So you can't identify these as rational numbers at the moment. And I say, let's look at these formal expressions, 1/2, 1 over 2, and 2 over 4. These are different as formal expressions, but we would like them to represent the same rational number, however we decide to define rational number. So we are identifying two formal expressions as the same mathematical object. The way you do that is with an equivalence relation. How exactly are rational numbers defined? Many people would say a rational number is a quotient, a over b, of two integers where b is not 0. That's not a formal definition. To define rational numbers formally, we begin with the set of all formal quotients, if you will, a over b, where b is non-zero. Equality among formal expressions is identicality, because they're formal expressions. They have no meaning. So you just have to look and make sure the atoms are the same in both cases. So 1 over 2 is not equal to 2 over 4 as formal expressions. Now, we want certain of these formal expressions, such as these two, to represent the same rational number. However, we decide to define rational numbers, so we need a different notion of equality, a notion that expresses equality of rational numbers. And as I said, we do that with an equivalence relation. So we define a relation on these formal expressions by saying A over B is equivalent to C over D if the cross products are equal. This is an equivalence relation, so it captures the essence of equality. It's not identicality, but identicality and equality are not the same. Identicality is kind of a physical concept, whereas equality is a mathematical concept. The idea is that we want two formal expressions to represent the same rational number if and only if those two formal expressions are equivalent. Well, this is leading up to the obvious question, yes, but what exactly is a rational number? The answer is that it's an equivalence class under this equivalence relation. So for example, the equivalence class containing 1 over 2 is the set of all formal quotients that are equivalent to 1 over 2, or put another way, B has to equal 2A. So it's this set, the set of all A over 2A. A is an integer non-zero. Well, you may be a little confused here because there is in fact a difference between the formal definition of a rational number, which I just gave, and the common usage of rational numbers. Even among mathematicians, in common usage, we simply think of each representative of the equivalence class as a rational number, the same rational number. So there's a forgiveness here. The informal version is fine, generally doesn't get us into any trouble, but there are occasions when we have to revert to the formal definition of rational number as an equivalence class, or at least keep that in mind in case we need it to clarify a situation. Okay, now let's get back to linear algebra. The reason that we've gone into this great detail concerning equivalence relations is because we need to define linear combinations. It's analogous to the problem of defining rational numbers. Now this discussion applies to all vector spaces, and we will return to it in the when we start linear algebra proper. But let's talk about what happens in R2 now, because this is a little involved, a little subtle. It wouldn't hurt to see it twice. Consider these three linear combinations in R2. All of these evaluate to the same vector, 5, 8. Remember, linear combinations are formal expressions. When we evaluate these, we get this vector 5, 8. So we can say these are all equal as vectors, not as formal expressions, but as vectors. But we want to treat the differences between these three linear combinations as not being equally important, and I'll show you what I mean. Look at the first two formal expressions, the first two formal linear combinations. They are the same except for the order of the terms. And in some sense, nobody cares about that difference as far as linear algebra is concerned. It's not just that they evaluate to the same vector. That's part of it. But we have no way to control the order of terms when we're adding vectors. And so it really is not important to us, or at least it better not be important because we can't control it. So we want to consider the difference between these two as unimportant or trivial. Another way to say it is that these expressions should be considered essentially the same linear combination. And that's for the purposes of linear algebra. They're not identical, so I don't want to say these are the same. We could say they are the same as vectors, but I prefer to say they are essentially the same linear combinations. On the other hand, if you look at the first and third of these linear combinations, these are different in some more profound way. You can't reorder the terms here to get from one to the other. There is something more profoundly different between these two linear combinations. So we don't want to treat them as essentially the same linear combination, even though they evaluate to the same vector. There's a more important difference. We can handle this situation in essentially the same way we did for rational numbers. We define an equivalence relation that expresses the unimportant differences, and then we can ignore them in a way. So here's the way it goes. Two linear combinations, L1 and L2 of vectors in R2, are essentially the same, and I'll denote that with a tilde. If we can pass from one of these equivalent linear combinations to the other using a sequence of 0 or more of the following operations: reorder the terms, insert or remove 0 terms equal to the 0 vector, an unimportant difference, combine or uncombine terms that involve the same vector. So these three operations, if you will, describe the unimportant differences between linear combinations. Any other differences are important. This is pretty easily shown to be an equivalence relation, and I'll let you think about that. Of course, if two linear combinations are essentially the same, they will evaluate to the same vector. The unimportant differences don't change the value of the linear combination as a vector. So if L1 is equivalent to L2, then L1 equals L2. Now this equality means equal as vectors. That's what we mean by an equal sign between linear combinations. They're the same vector. They're not identical in general. But the converse of this is false, and we've seen that pretty much. If you take these two linear combinations, they do evaluate to the same vector, so they're equal, but they're not equivalent, because no amount of reordering of terms, including or removing zero terms, or combining or uncombining like terms, can turn one of these into the other. So they are fundamentally different, or we will say essentially different. So we have two distinct equivalence relations on the set of all linear combinations of vectors in R2. We have equality as vectors, which everybody calls equality and uses an equal sign. And we have essential sameness, essentially equal, essentially equivalent. Equivalent under the equivalence relation that we've just defined. The most important problem related to equivalence relations is that of finding a way to determine when two elements of a set are equivalent. Or put simply, finding a test for equivalence. And there are two common approaches that attempt to deal with this issue: canonical forms and invariants. And both of these will prove extremely important to us in the latter part of this lecture series. Let's begin with canonical forms and take a look at the definition. Here's a set. Here is a partition into equivalence classes. So we have an equivalence relation here. A subset, which I called capital C, of the set S, with the property that each equivalence class contains exactly one member of C. Exactly one member is called a set of canonical forms. Another term is system of distinct representatives. In a way, that's a nicer term because it seems a lot more descriptive. A system of distinct, meaning one each, representatives of the equivalence relation. If C is a set of canonical forms, and if we take an element from the set, let's say little s, then the unique element C sub s of the set of canonical forms that is equivalent to little s is called the canonical form of S. Or we say that S has canonical form C sub s. The word canonical means standard, so it's standard form. Okay. So this is the formal definition of a set of canonical forms and a canonical form. Now, if we can find a method for determining the canonical form of each element, we've got a test for equivalence. Namely, two elements are equivalent if and only if they have the same canonical form. So we've turned equivalence into equality. Now this will only be a practical test if we can find a practical way to determine each element's canonical form. And that can be extremely difficult. So let's look at some examples, two really important examples of canonical forms in linear algebra, in matrix theory, in fact. Two matrices of the same size m by n are said to be equivalent and denoted by 3 bars here if there exist invertible matrices, P and Q, of the appropriate size, so we can do this multiplication, for which B equals PAQ. P and Q must be invertible. There's another way to express matrix equivalence. And incidentally, the term equivalent is the terrible choice here because that's a generic term for any equivalence relation. So it probably would be better to say matrix equivalent every time, and I'll try to remember to do that. Another way to phrase matrix equivalence is to note that every invertible matrix, such as P and Q, is the product of elementary matrices. So pre-multiplying A by P is equivalent to pre-multiplying A by a sequence of elementary matrices, which is equivalent to applying a sequence of 0 or more elementary row operations to A. And similarly, post-multiplying by Q is equivalent to applying a sequence of 0 or more elementary column operations. So we can say that two matrices, A and B, are equivalent, a matrix equivalent, if and only if A can be reduced to B by performing elementary row and or elementary column operations. Now, the matrix, which I'll call R, that is obtained by reducing A to both reduced row echelon form and reduced column echelon form, which you do using elementary row and column operations, is equivalent to A. But it's not hard to see from the definitions of reduced row and reduced column echelon form that such a matrix must look like this. It has the identity in the upper left corner and zeros everywhere else. And the dimension of this identity portion, R, is in fact the rank of this matrix and therefore the rank of A. So every matrix, I'll call these the J matrices. So every matrix A is equivalent to at least one of the J matrices. Matrix equivalent. But no two distinct J matrices can be equivalent because of the same size, of course, because they have different ranks. And matrix equivalence preserves the rank. So the set of J matrices of size m by n form a set of canonical forms for matrix equivalence. And that gives us our test for matrix equivalence. A and B are matrix equivalent if and only if they have the same J matrix. And this is actually a very practical test because we can take a matrix A, reduce it just to row echelon form, read off the rank, and that'll give us the J matrix. You might be wondering why not just use the rank rather than the J matrix. Well, we'll talk about that in a few minutes. The rank is an invariant. The J matrix, the corresponding J matrix, is the canonical form. Sometimes one is easier to deal with than the other. Let's look at another example that's actually much more complicated and will occupy a great deal of our time in the latter part of the course. Two square matrices of size n by n are said to be similar, and I'll denote it with a tilde, if there is a single invertible matrix P for which B equals P inverse AP. This too is an equivalence relation. Now, however, when it comes to finding a set of canonical forms for matrix similarity, life gets a whole lot more complicated. And the reason is that matrix similarity is much more restrictive than matrix equivalence. To obtain similar matrices, the two matrices on either side of A, the P and Q is what I called them before, now have to be related. They have to be inverses of each other. This means that in general, we are no longer free to put the matrix A in both reduced row echelon and reduced column echelon form at the same time. You can do one or the other with P or Q, but that's going to get screwed up. To be more specific, suppose that, for example, we apply a single elementary row operation to the matrix A using an elementary matrix E. So we form EA. To maintain similarity, we then have to multiply EA on the right by E inverse. So what we did to the rows of A determines what we must do to the columns. For example, if pre-multiplying by E had the effect of, say, multiplying the kth row by a non-zero scalar R, then post-multiplying by E inverse has the effect of multiplying the kth column by 1 over R. So we are much more restricted. We don't have the same freedom that we had before. We can't apply elementary row and column operations independently like we could under matrix equivalence. As we'll see much later in the book, there is a canonical form for similarity. It's called rational canonical form. Unfortunately, it's quite complicated and not always easily obtainable, so its practical value is very limited. It has theoretical value, to be sure. There's also a canonical form that applies only in special cases. It applies to complex matrices, but not to all real matrices. It's called Jordan canonical form. It's a much nicer looking matrix than the rational canonical form. But because not all real matrices have a Jordan canonical form, that puts a cramp in it. Both types of canonical forms are more of a theoretical tool than they are of a practical one. Let's take a look at invariants. It's a similar concept, really, actually a little more general than canonical forms. Here again is a set S with an equivalence relation the equivalence class is showing. A function from S to some other set, may have nothing to do with S, is called an invariant under this equivalence relation if it is constant, same value, on the members of each equivalence class. So you can see the arrows here. They're all going to the same value in each equivalence class. And here it is in symbols. A equivalent to B implies f of A equals f of B. Now, one possibility is that F sends everything in S to a single, say, 0. That's an invariant, but it's a useless invariant. A function from S to X is called a complete invariant if not only is it constant, but it's a different constant on each equivalence class. So we have a biconditional, A equivalent to B if and only if f of A equals f of B. Complete invariants form another test for equivalence, then, because of this biconditional. Some examples, as we discussed, the rank of a matrix is as a complete invariant for matrix equivalence, because two matrices are equivalent if and only if they have the same rank. They have the same J matrix, which is equivalent to saying they have the same rank. So here's the complete picture for matrix equivalence. The set of J matrices is a set of canonical forms. The rank is a complete invariant. A very nice picture. It's relatively simple, easy to deal with. Take a look at these two matrices, for example. They have the same rank, rank 1, so they're equivalent. That's a lot easier than demonstrating equivalence by producing the matrices P and Q. As to matrix similarity, life is a lot more complicated. There are a great many invariants for matrix similarity, also called similarity invariants, but none of the ones that we're going to encounter in this book until the end are complete. To illustrate, here is the definition of similarity. If we take the trace and we use this cyclic property we talked about earlier, we'll see that the trace of A and B are the same. That means that similar matrices have the same trace, and so the trace is a similarity invariant. But these two matrices happen to be similar, and I'll let you verify that, but they have different traces. I'm sorry, I'm getting a little tired. Backwards. These two matrices have the same trace, but they're not similar. So the trace is an invariant under similarity, but it's not a complete invariant. The determinant also is an invariant. If two matrices are similar, they have the same determinant, but the converse is not true. These two matrices have the same determinant, but they're not similar. Well, you might be wondering then, what good is an invariant that's not complete? A non-complete invariant can never be used to show that two elements are equivalent. This just doesn't tell us anything about equivalence, but it can sometimes be used to show that two elements are not equivalent. For example, if the traces of two matrices are different, then the matrices are not equivalent. If the trace of matrices is the same, it tells us nothing. So invariants that are not complete are still useful, quite useful. They're just not nearly as useful as we would like them to be. One final note. If C is a set of canonical forms for an equivalence relation on a set S, we can easily turn that into an invariant, a complete invariant. We just define a function that takes each element of the set to its canonical form. So canonical forms are a form of invariant, but invariants are more general because the function can have any codomain, any set X, like the rank, for example. So the idea of an invariant is somewhat more general than the idea of a canonical form. Okay, we are, as I said, going to spend a lot of time with equivalence relations, with canonical forms, with matrix similarity. So you might want to repeat this video if some of this material is not quite clear.